algorithm, which is Dijkstar's algorithm. This algorithm is used to find the shortest path. Why? If we are having multiple nodes, right? So if we are having multiple nodes, this algorithm used to find the shortest path from our source node. So basically, we will be having one source, only one source. From this source node, what is the shortest path to travel to each of the node? This is calculated by Dijkstar's algorithm. So let me repeat it again. From a single source, when we have to find the shortest path to all the other nodes, then that algorithm is called as Dijkstar's algorithm. How we will solve that? We will see it later, but the main objective of this algorithm is to find the shortest path from a single source to all of the other nodes. Guys, the the algorithm path is too much big. Like in my notes also, it's like one page where I have written everything in short forms. So if I just write the algorithm, if each and every line of it will bounce on top of your head. So first I will say you the approach. Listen it very clearly, very clearly, very clearly. If you are having any doubt, you ask it then and there itself. So in this, what we will do is we will use relaxation concept. What is relaxation? The relaxation concept is if du plus c of u comma v is less than d of v, at that time what we have to do, we have to update our d of v to d of u plus c of u v. This is our relaxation. So this piece of code is there, right? These two lines of code, entire Dijkstar's algorithm is dependent on these two lines of code. So understand this one very properly. So now let's take an example. Assume we are having A, B, C. Again, the cost to go from A to B is 20. The cost to go from B to C is 10. And the cost to go from A to C is 40. Now what we have to find out, let's assume A is our source, okay? So A is our source. Now what we have to find? We have to find the shortest distance which is required from A to B, which is required to travel from A to B, from A to C. Okay. So first, what we will do, we will see the relaxation concept, this one code. So first step, what we'll write, we will take this as U, this as V, before taking U and V. So guys, one logical question. You are at D, okay? You are at this one, source A, and you want to travel to A. So what is the distance? So you are at A, you want to travel to A. What is the distance? The distance travel would be 0, right? So basically you are at the same distance, source and destination is same. Similarly, when it comes to B and C, we don't know yet what is the shortest path. So what we will do, we will write it as infinite. We will write it as infinite. We don't know it, so we will write it infinite. Now what? Now let's consider this. Now let's consider this one as U and this one as V. This one as U and this one as V. Now what we have written here? Just see the relaxation. So d of U. What is the d of U? The distance of U. The distance of U is 0. 0 plus. What is the cost of u to v? So cost of u to v is 20. 20. If this is less than d of v, what is the case? D of v? D of v, distance of v is infinite. So if this condition is true, here we can see 0 plus 20 is 20. 20 is obviously less than infinite, right? So at that time, what we have to do? We have to update our d of v. What we have to do? We have to update our d of v as what? D of u plus c of uv. What is d of u? D of u is 0. 0 plus 20. We have to update our d of v as 20. So now, our new d of v, d of this will be 20. I'm facing too much latency with my pad. Let me try it with this. Okay. So our new d of v will we have written. So now what we will do? We will create a new u. We will take our new v. Okay. Now let's see our relaxation. What is d of u? D of u is 20. D of u is 20. Oh, this latency is from Mega website itself. When I'm using my laptop's touchpad, then also the latency is there. Okay. So d of u is the distance of u, which is 20. We will add with cost of u to v. So cost of u to v, what we are having the cost of u to v? 10. 20 plus 10. Oh, we cannot try it directly. Wait. So when we take uv, when we take u and v here, after this what we have to do? We have to take our v here. We have to check from u all the possible directly connected links. So from A directly, one of the directly connected link is B, another one directly connected link is this one. So we have to check this one, this and this. This is just an example. I will show you guys with one big real example. We should not find it like this. There's another one method. This is just to understand you guys. Okay. So now we will take this one. So what is d of u? D of u is again 0 plus what is cost of u to v? Cost of u to v is 40. If this is less than d of v, what is d of v? Infinite. If this is less than d of v, what we have to do? We have to update our d of v with d of v plus c of v, which is 40. So this cost was 20, we have updated it, and now we have to update our this cost also with 40. Then what we will do? We don't have any other ways, we don't have any other directly linked with it. Now what we have to do? We have to update our u. We will update our u and we will go our u here. Next we will take this v. Now what we will do? We will again see our relaxation. What is our relaxation? D of u. What is d of u? D of u is 20. 20 plus. What is our c of u? C of u is 10. 20 plus 10 is 30. If this one is less than d of v, what is d of v? 40. So if this is less than the condition, then what we have to do? We have to update our d of v with d of u plus c of u, which is 30. So now our new distance at c is 30. So again, we don't have any directly linked from B also. That's why there's no V. When we come this here, we can't go, right? there's no nothing link from C. So that's why we will end our iteration, and these are our answers. So from A, the minimum distance, the shortest distance required to go from A to A is 0. From A to B is 20. From A to C is 30. Like this, we can write our Dijkstar's algorithm. Let's take one big example and then see. So in this big example, I will show you guys one more method to write it. If there are any engineering students and having syllabus in syllabus this algorithms, then in main exam you are not asked to write the like coding part. Okay, so in theoretical exams they will not obviously ask to write the coding part algorithms. You have to drag in the questions. You have to drag in the questions and write the topological sort, or sometimes write show the whole method how you have to drag and it. A to B. Let's take here we are having C, here D, so this cost is 14, this is 2, this is 9, this is 6, this is 11, this is 15, this is 10, this is 7, this is 9. So this is our given graph. Now what we have to do, we have to find our the source is this one E. Okay, this is our source. So our source is E, and just write, let's get all the remaining thing A, B, C, D, E, F. Okay, so let's start. Our E is there, and initially we will put all the distances as infinite. We can directly write the distance of E as 0, right? We don't have to find it using some algorithms. You can directly write it, the distance of E as 0. So now what we have to do, we have to check first. Let's check this one, E and F. Okay, so first let's go with this itself. A, from E, only E, can we go to A? Yes, we can go to A. What is the cost? Cost is 14. 14. From directly E, can we go to B? No, we are not having any direct link at that time. Infinity, the same infinity will be retained. Next, from E, is there direct link to C? No, again we have retained our infinity. From E, do we have D? Yes, the cost is 9. From E, do we have F? Yes, the cost is 7. After completing our first iteration, what we have to check? We have to check the minimum number. What is the minimum distance? So here, what is the minimum distance? Our minimum distance is 7, which is F. So now this is our final answer for this F. It cannot get more shorter than 7 from E to F. So we have to add that in our answer. E, F. Previously we had answer for only E. Final answer for E is 0. Now we got the final answer for F, which is 7. So now we have to check all this pass by our final answer. So now can we go to A? From E to A, again only 14. This is the shortest path. Next B. So by using E also we can't go, by using F also you can't go. So again we will retain our infinity. Let's come to C. So previously we couldn't go from E to C, but via F we can go to C. What is the path? 7 plus 15. What is 7 plus 15? 22. 22. Let's come to D. So previously we got to D with cost 9. Now via F we can get with cost 17. But which one is smaller? 9 is only smaller. That's why we will retain our old answer 9. Next, this answer we already got. We'll get it as it is. Or we will just not write only. When we got the answer, we will circle it and we will not use it, write it again. Just to save our time. Here now which is the smallest one? 9 is the smallest one. That's why what is it? D. So we got answer for our D also. E, F, D. So next what we have to check? We have to check A. A. Directly if we went to E to A we got 14. But via D if we went, how much we'll get? We'll get 9 plus 2 11. So which one is what shortest? That one will get. Okay. Next B. So via D we can't go, right? To using D also we can't go directly to B. E F D we are having only E F D. Like this we can't go. So at that time again we will retain infinity. Next C. So C is here. Previously we went like this. Now we are having, we can go like this also. We are having D. So 9 plus 11. What is 9 plus 11? 20. 22 is smaller than 20 is smaller than 22. So 20 distance we will be having here. So 9 is, we got our final answer here only, right? So in this what we have to check? In this we have to check the smallest one, which is 11. So we got our answer, one more vertex in our answer. E, F, D and A. So now let's come to B. So by using E, D, F and A, what is the shortest path to go to A? One is E to A to B. Another one is E to D, D to A to B. So 9 to 11, 11, 9, 20. So this is the shortest path. If you go like this, 14 plus 9, it would be 23. So this is the shortest path. What is the answer? 20. And C. By using D also, by using F also, A also, what is the shortest path? 9 plus 11 only is the shortest path. We can't go 14 plus 2, 16, 16 plus 11, 27. This is the shortest path. So here also 20 is the shortest path. So we got the total answer. If there was if these two values were not the same and there was one shortest value, at that time what we will do? We will circle the shortest value and again find the good. But here both are same, so we got a final answer for this also, this also. So now what is our answer for distance? Distance of A would be 11. That means from E to A, the shortest distance we can travel is 11, like this, via D. So what is the shortest distance from E to B, which is 20, E to C is 20, E to D is 9, E to F is 7. So these are all our distances and this is our answer. So this distance again which is there, right? This distance again, D again, we need to return. So this is our Dijkstar's algorithm. If you are having any doubt, you guys can ask. In video exam also what you have to do, you have to write, you have to draw this graph, you have to write this table, and I guess you have to write this one also. You have to draw it like E F D. Big is A is there, B is there, C is there. A is here, B is here, C is here. So how will you go from E to A? E to A 11, E to A 11 via D. So via D you will go to E to A. How will you go to E to B? E to B 20, which is like this, which is E to D, E to C. What is it? E to D, E to D, D to A to B. This is the shortest path. How will you go to C? C is also 20. We will go from E to D, D to C. How will you go to D? D will go like this only. How will you go to E? E you are having here only. F you are having here only. So this is our final answer. What we have did, we have eliminated the unnecessary edges. So we have eliminated this edge, we have eliminated this edge, we have eliminated this edge. So where we will use it in real world? In real world we will use it in navigations, in maps. So to find the shortest distance between one source to destination, we will use this algorithm. And next one we will use this in networking. In networking also, when we will be sending our packets, we need to find out the shortest path, right, to send our packets at a very low latency and very fast quickly. That time we will use this algorithm. I hope you understood this algorithm. Now what are the drawbacks of this algorithm? The drawbacks of this algorithm is this is only valid, this will only give us correct answer if this cost is positive. Suppose if this cost is negative, at that time it won't work well, it won't give us the accurate answers. So there are few cases where there are few scenarios in real life also where we will get our weight as negative. Okay, at that time this algorithm won't be satisfied. So to satisfy that type of questions, what we will use, what we have to do is we have to use our next algorithm, which is Bellman-Ford algorithm. Bellman-Ford. So I have already said what it is. This is also same as Dijkstar algorithm. The objective is same. We have to find the shortest path from a source node to all the other nodes. But this is more efficient in a ways where why? Because in this algorithm we can have negative weight also. So in this Bellman-Ford, if we are having negative weight also, we can use this Bellman-Ford. And one more test use cases of this Bellman-Ford is when we have to check if we are having a negative cycles in our algorithm, in our question. So when we get a graph, if you want to check that if that particular graph is having a negative cycles or not, then also we can use this Bellman-Ford algorithm. So let me just explain you guys this algorithm. If you understood previous algorithm, this is very simple. This is very small, very simple. So and this also we have to relax. So the condition is we have to relax each edges v minus 1 time. So what we have to do, we have to relax each edges v minus 1 time. So for example, they have given A, B and C. And the weights they are given as 10, 5 and as I said a negative weight 8. Okay, so what would happen in previous algorithm? In previous algorithm it is given as 10, it is given 5 and that's it. So the cost from A to B is 10, the cost from A to C is 5. It will give that much itself. But what is the actual answer? We can go from A to B, B to C also, right? 10 minus 8, 2. So previously what it will do, it will just see this 10, this 5. So 5 is shortest. It will just consider this one itself. It will not go from here and check. in previous. But here we'll just go here and check. That's it. That's the difference between Bellman-Ford and Dijkstar's algorithm. Dijkstar's algorithm is very fast when compared to Bellman-Ford, but it will be not useful if we are having negative elements. When we are having a negative element, we will use Bellman-Ford. If we are not having negative elements, then we will use previous one, which is Dijkstar's algorithm. So now let's drag on it. So we have to relax each edges v minus 1 time. So what we will consider, let's consider A is our source. A is our source. Let me darken it. Now the distance from A to A is, the distance from A to A will be 0 itself. The distance from A to B, let's first consider infinity. We have to relax it v minus 1 time. So what is v? V is number of vertices. Here how many vertices are there? 1, 2, 3. Here we are having 3 vertices. So how many times we have to relax? We have to relax 2 times. So when we relax one time, so what we will check? Same, the relaxation concept. Previously what we did, the distance between these two. So 0 plus 10. If 0 plus 10 is less than infinity, yes, the condition is true. At that time we will update this one as, at that time we will, the initial values are same. A is connected to B is connected to C. So now what we have to do, we have to update this one as 10. Why? Because the condition 0 plus du plus c of u comma v is less than d of v is true. At that time we have to update the d of v is equals to d of u plus c of uv. So in simple words, if this is 10, we will get 10. That's it. So when it comes to this side, it will become 5. So this is our R1. We have relaxed it one time. Next what we have to do, we have to relax it again. Why? Because we have to relax it 2 times, v minus 1. So when we go to relax it second time, what we will see, the initial graph is same, A, B, C. Now what we will check. So first we will check this. So what is the distance from this to this, including this? So it will be this one itself. Let's go to here. Okay, we will go here, and there are to reach C. There are 2 ways. We can reach directly from A. We can reach from A to B and B to C. But when it comes to B, right, there is only one way, A. So that's why our final answer is 10 itself. But for C, we are having 2 ways. We will check the second way also. A to B, B to C. So what was the cost from A to B? Which is 10. What is the cost from B to C? That is minus 8. So 10 minus 8, the answer is 2. When we compare 2 with 5, which is smaller, 2 is smaller. So we will get 2. So after relaxing 2 times, which is v minus 1 times, now we got our final answer d as 0, 10 and 2. So from A, the shortest distance to go to A is 0. From A, the shortest distance to go to B is 10. For C is 2. So this is our final D answer. What we used? We used our Bellman-Ford algorithm. So I also added a line in Bellman-Ford algorithm that it will detect negative cycles also, right? So how does that work? How we will detect negative cycles and what are the examples of negative cycles? I'll show you that. To detect negative cycles, what we should do is we have to relax v times. So previously to get answer what we did, we just relaxed v minus 1 time. To detect negative cycles, what we will do, we have to react one more time. We have to relax one more time. When we relax one more time, we will just get to know if we are having negative cycles or not. How? I will show you in this same particular previous example itself. How? By relaxing it one more time. If we relax it one more time, A, B and C. So 0 will remain 0 itself, 10 will remain 10 itself, 2 will remain 2 itself because there are no more paths. So again you can see if we go on relaxing n number of times, n plus number of 1 times, like so many number of time also we will get the same answer. So at that time we are not having any negative cycles. But just by relaxing one more time, if we got the changes in the values, suppose this changed to 8 or this changed to 2 or something or the other thing, if we are seeing a changes in our distances, then we will say that we are having negative cycles. Let's take an example which is having negative cycle and see A is connected to B is connected to C. The cost here is 10, 20 minus 30. So what we will assume? We'll assume the initial distance is 0, infinite, infinite. We'll do the arg1. Then we will do the arg1. A is connected to B is connected to C. I'll just write like this C. Okay. So when we do the arg1, we'll just take one step. Previously it was 0. Here from A we can go to only B. So what is the cost? 10. So 0 plus is 0 plus 10 less than infinity? Yes. So we will update this also. 0 will become 10 in arg1. Apart from that, it will remain infinity. When we go to arg2, what will happen? This infinity will also convert into 20. So again, if we go to arg3, so ideally we have to stop till arg2, right? Ideally we have to stop till arg2 to get our answer. But if we go to arg3 and check, so when you go to arg3 by using A, B and C, we are having one more path, which is this path. So what is the cost of this path? Which is minus 30. So 10 plus 20, 30. 30 minus 30, 0. So we have to write this distance as 0. So the output which you got from R2 and the output which you got after R3 are not same. At that time we can say that this particular example is having negative cycle. So what do you mean by negative cycle? Just write R4, R5, R6, you will get to know it. So you have 0. Next what you will do? You will again check this. So when you again check this, what will become the distance? It is 0. 0 plus 20, it's become 20, right? It will be 20. Now what we'll do? You'll write here 20 minus 30. 20 minus 30, it will become minus 10. So again minus 10 here, it will become minus 10. Minus 10 minus 40, it will become minus 40. So like this minus 60. It will goes on increasing negative elements. This cycle won't stop. So that's why this is called as negative cycle. So when we have to detect our negative cycle, we will just relax our given question, relax our given graph v times. If we just want our distance, what we have to do? We have to relax our edges v minus 1 time. This is our Bellman-Ford algorithm.